Bismillahirrahmanirrahim. Assalamualaikum. My name is Nur Aini binti Abdul Wahab. I would like to present the progress report for my project entitled Microplastic Removal in Synthetic Wastewater through Electrocoagulation Utilizing Porous Nickel Fe Electrode. And I am currently in my second semester under the supervision of Dr. Nur Ain Isa and co-supervisor Dr. Iza Sazanita Isa. The content of my presentation today will include the following 8 points. Introduction. Microplastic are tiny plastic particles with size less than 5 millimeters. They have higher surface area to volume ratio. They have low density. They are stable and buoyant, which means that they can travel on sea surface. There are two main sources of microplastic, which is the primary microplastic, which usually can be found in the product such as cosmetic and household product. And then we have the secondary MPs, which are resulting from the degradation of larger plastic product. Okay, the current situation with microplastic is that in 2016, it is estimated about 19 to 23 million metric tons of plastic has been released into the water system, and is expected to increase up to 53 million metric tons in 2030. And then among these plastic release, 60 to 80% are microplastic. The problem with microplastic is that they absorb toxic substances and can be ingested by microorganisms and can accumulate in food chain and reach human. They can transport contaminant to less polluted area. And then the wastewater treatment plants is seen to be ineffective and inefficient in removing microplastic. The current removal method that has been used is, among others, filtration and separation, adsorption, and electrocoagulation. Electrocoagulation is an electrochemical water treatment process used to remove contaminant from wastewater and industrial effluent. It works by application of electrical current to the metal electrode, and then from there it can help to create coagulant. This is the first step, and then the second step is the destabilization of contaminants to form flocks, and the third step will be elimination of flocks by flotation and sedimentation. The advantages of electrocoagulation is that it is simple, low cost, it produces less secondary pollutant, it produces less sludge compared to chemical coagulation, it can be easily automated, and it can produce coagulant in situ and effective in capturing pollutant. However, the limitation are the commonly used anode or the conventional electrode of iron and aluminium form high quantity of sludge, and there is a requirement for electrode replacement due to dissolution of the electrode and also passivation of electrode, which lead to high cell voltage, and in some cases it is very hard to separate the flocculant. For problem statement and objective. Okay, this research come up with 4 problem statement to relate with 4 objectives. The first problem statement is that conventional electrode suffers limitation of high sludge generation and prone to passivation, corrosion, and degradation over time. To overcome this limitation, there is a need to develop a new electrode. So my first objective is to fabricate a porous nickel Fe electrode through electrodeposition by varying the nickel Fe ratios and characterize the electrode. Okay, the second problem statement is the need to have in-depth information on the porosity characteristic, as it is believed a porous electrode facilitating more efficient removal of MPs and reducing electric power requirement. However, the traditional method for porosity analysis are time-consuming, destructive, and expensive. Thus, new method for porosity analysis are highly needed. So my second objective is to investigate the porosity characteristic of the nickel Fe electrode in terms of pore diameter, porosity percentage, and pore depth using image processing technique. Okay, the third problem statement is the use of porous nickel Fe electrode has not been widely applied. Thus, the performance of this electrode in the EC process, specifically in MPs removal, remain largely unknown. Comparative studies between porous nickel Fe electrode and conventional Fe electrode are also lacking. So, objective 3 is to evaluate the performance of the porous nickel Fe electrode in the removal of MPs via EC by investigating the optimal operating condition, contact time, and MPs concentration, and comparing its EC performance with the conventional Fe electrode. Okay, and then the last problem statement is the formation and behavior of flux are critical factors influencing the efficient removal of MPs during the EC process. However, there is a lack of comprehensive research on the characterization of flux properties and their correlation with MPs removal efficiency. So the last objective will be to investigate the characteristic of flux form and their relationship with the efficiency of MPs removal in terms of flux morphology, composition, amount, size, and settling velocity. Scope of study. This study will involve 4 phases, which is phase 1, the preparation of nickel Fe electrode and its characterization. Phase 2, investigation on the porosity of the electrode. Phase 3, evaluation on the EC performance of nickel Fe for MPs removal. And phase 4, investigation of the flux characteristic. Next will be the literature review. Table 1 summarizes data from various studies that shows the type and percentages of microplastic found in wastewater along with their size ranges and shapes. The most common type found were PP, PE, and PET, with different percentages in wastewater across the studies. The size of MPs range from 1.5 micrometer to 5,000 micrometer, and they were mostly present as fibers, fragments, and microfibers. The data highlights the diverse nature of MPs in wastewater and the importance of understanding their characteristics for effective management and removal. And then the structure of polypropylene is shown in this slide, and it is one of the most commonly found MPs used in plastic packaging, pipes, and bottles. Next is electrodeposition. It is a surface modification widely employed involving the deposition of thin layer of the material onto electrode surface. It is low cost, simple operation with high efficiency method for surface modification, and it can protect the underlying electrode material from corrosion and passivation, thus improve electrode stability and reduce the need for replacement. And then the deposited material may provide more active site for the EC process, thus increasing the overall efficiency of the electrode. Okay, table 2 shows the preparation of nickel Fe electrode by electrodeposition to create various electrode structures for different electrochemical application. Nickel and iron, nickel and Fe, were commonly used as electrode material with parameters optimization including pH levels, current densities, deposition time, and nickel Fe ratios. The electrode prepared through ED exhibited enhanced activity and stability with highly porous and well-distributed structures. The result demonstrated the potential of ED as a versatile technique to tailor electrode structures for specific applications such as alkaline water electrolysis and pollutant removal. For porosity analysis, accurate measurement and characterization of porosity are crucial for understanding the behavior and performance of porous material in various applications. However, traditional methods such as mercury intrusion porosimetry and gas adsorption has been widely used but come with certain limitation, as it is a destructive technique and then requires specialized equipment and not suitable for in situ measurement. So, to overcome this limitation, researchers has increasingly shifted their focus to image analysis for porosity measurement. Image analysis allows non-destructive examination of the internal structure of porous material, providing valuable insight into their pore size, pore shape, and distribution. So, from table 3, we can see that table 3 shows that the research on porosity analysis using image processing, where it is able to provide properties such as pore diameters, size distribution, pore density, and percent porosity. This slide is on the research on the electrocoagulation of MPs. Table 4 shows the removal of various types of MPs by using conventional electrode. The optimization parameters included pH, current density, electrolyte concentration, and also retention time. The removal efficiencies varied between 85.4% to 100% under different operating conditions. This finding demonstrates the potential of electrochemical methods for efficient MPs removal with different electrode materials and operating condition, playing a crucial role in achieving high removal efficiencies. This is the overall methodology for this work, where it will be divided into 4 stages and to relate it with the 4 objectives. The first stage is the fabrication of porous nickel Fe electrode via electrode deposition, and also the characterization of the nickel electrode. These are the parameters that will be used. And then in stage 2 is the investigation of the porosity of the nickel Fe electrode using image analysis. The porosity analysis involved with the pore size, percent porosity, and also pore depth. And then in stage 3 is the evaluation on the removal performance of electrocoagulation using nickel ferrum electrode, and to identify the best performance electrode. The parameter of the electrocoagulation is given here. And then the last objective is the flock characterization. So we will investigate the flock characteristic in terms of its morphology, composition, structure, flock amount, and settling velocity. Okay, this slide shows the overview of research work which relate between the problem statement, objective, methodology, and also activity in the methodology. Okay, for result and analysis. For microplastic characteristic, the structure and morphology of polypropylene microplastic PPMPs is shown in figure 8 and figure 9. So the observation is given under the observation under the optical microscope reveal several PPMPs appear as white particle with irregular shape. The irregularity in their morphology suggested that they had undergone degradation or fragmentation, which is usually observed in the aged MPs. Okay, and then SEM analysis also has been conducted on the PPMPs, and the result shows a surface structure characterized by a rough, shred-like appearance with visible cracks. The rough surface observed in the SEM images is likely a result of weathering and mechanical abrasion over time. This rough surface and crack on MPs may enhance their interaction with metal hydroxide flocks formed during EC and increasing the chances of effective microplastic removal. Okay, this slide shows the microplastic size distribution. The size distribution analysis was carried out based on statistical parameter of the 334 dataset of the individual measurement of PPMPs. Okay, figure 10 shows particle size distribution of the MPs with normal distribution curve. The smallest recorded size of PPMPs was 14 micrometer, while the largest PPMPs measured 96 micrometer. So give ideas the range of PPMP size present in these studies, with the mean value of 50 micrometer, which indicates the central size around which most of the PPMPs are distributed. Okay, this is the FTIR of the PPMPs. As we can see here, the peak which are the characteristic of polypropylene can be seen at 2952, 2915, and also 2846, and also at 1456 and 1375. However, there are one extra peak at 2360, which refers to the presence of carbonyl peak, which indicates the possible existence of carbonyl group, which can be the result from oxidative degradation of the HPPMPs. So next is microplastic dispersion in water. So dispersion of MPs help distribute MPs more uniformly in water, making it more possible to capture them more efficiently during the treatment process. So this can be done by adding sodium lauryl sulfate, SLS, which is a surfactant commonly used as dispersing agent, and it can help to disperse hydrophobic substance like MPs more uniformly in water by breaking down clump and preventing aggregation. So in this graph, the turbidity reflects the effectiveness of SLS concentration in dispersing MPs while minimizing disturbance to turbidity level. So as you can see, the turbidity value for 2% and 5% SLS shows fluctuation over time with higher turbidity values compared to SLS, where the concentration of the SLS might be insufficient to effectively disperse the MPs. Fluctuation in turbidity values indicate possible disturbance to turbidity, potentially affecting the dispersion of MPs. However, the turbidity values of 4% and 3% shows fluctuation trend for the first 5 minutes and then remain relatively stable with value closer to the turbidity of the SLS. This shows that the SLS concentration of 4% and 3% provide better dispersion of MPs in water. A stable trend in turbidity suggests effective MP dispersion with minimal disturbance to turbidity reading. Okay, this is the Gantt chart of my research work for 3 years. And this is the status for publication and thesis writing. And this is the planning for next semester. That's all. Thank you.